Speaker of the morning is Nam-Gyu Kang from Seoul National University, and he's going to talk about Radial SLE martingale-observables.
This is student work with Nikolai Makarov. Thank organizers for inviting me to this lovely place. Okay, at the very early stage of my PhD life, Peter, my advisor, introduced this Mandelbrot conjecture to me as a PhD topic, PhD dissertation topic, and I couldn't do anything for a whole year. And after that year, he tried to encourage me and told me that this conjecture is too difficult, and he thinks that this cannot be solved by the end of 21st century. And then after a few years later, of course, this Mandelbrot conjecture was proved by Greg and Oded and Bendelin. And of course, without these three heroes, many of us in this audience would not exist as we are. Okay, with Nick Makarov, I implement a version of component field theory in Koda case and in the radial case, and we define the fields in component field theory as certain types of focus space field with tense nature, and also we treat a stress tensor and the bilateral field in terms of Lie derivative, which we borrowed from Riemannian geometry. And in this talk, I'm going to outline the difference between the Koda component field theory and radial component field theory of Schramm-Levin evolution. To do this, I need to introduce background charge modification of Gaussian free field and boundary condition changing modification. To introduce this one, I need to tell you about so-called one-leg operator as an OP exponential of Gaussian free field. Then there are two neutrality conditions on charges on these OP exponentials. One for the linear combination of bosonic fields to be a well-defined focus space field, and the other condition is for the Coulomb-Gas correlation function to be conformally invariant. So we have two different neutrality conditions, and to reconcile these two neutrality conditions, we need to place the background charge at the target point of SLE curve. And then I'm going to tell you about the relation between component field theory to caudal SLE and radial SLE. And this approach can be extended to various patterns of insertion, for example, n-leg operators for the multiple SLEs, component field theory of multiple SLEs, and fusion rules, and also several conformal settings, for example, dipolar component field theory and twisted radial component field theory. And also, it is very useful to describe classical limits of multiple SLEs. Okay, so the physicist's dream is the following. So they want to construct measure on fields on component field theory such that this correlation function is an expectation of this field as a random variable. But this is not successful so far. So I'm going to project this component field theory into the SLE level. So that the fields in the SLE level is a well-defined random variable as a local martingales. And the other approach is the following. So I'm going to approximate this field by random functions in the discrete level, and that level, these fields are genuine random functions, and measure is well-defined, and this correlation, this expectation will converge to these correlation functions. So for example, we use Geneva eigenvalues to construct approximated Gaussian free field and derivative of this Gaussian free field, and so on. So for example, expectation of approximate Gaussian free field at two different points converges to this correlation function of Gaussian free field as these 2 points are well separated. So, I think I can skip this notion of Gaussian free field because everybody knows about it. But let me explain this picture of this approximation of Gaussian free field, phi sub n. That's the approximation of Gaussian free field phi. So that's the difference of two Green's functions with singularities at lambda j's and mu j's. So these are independent Ginevra eigenvalues. Because I take the difference, I take the difference because if I take the difference, then expectation of this one is equal to 0 because these 2 points are independent. So lambdas are Ginevra eigenvalues of the Ginevra ensemble, and mu j's are independent copy of this. And this Ginevra ensemble is the n by n random matrix whose entries are IID complex Gaussians with mean 0 and variance 1 over n. N is the size of this matrix. Then it is well known that if you apply the test function f, then this phi sub n of f converges to phi of f. So it means this phi sub n converges Gaussian free field in distribution in law. So here is a picture of Ginevra eigenvalues with n 4096, and on the right hand side you will see the picture of uniform points. So then you can see there's a lot of gaps around here and here. So these Ginevra eigenvalues, in some sense, more uniform than this uniform point. So because of this phenomena, I took the Ginevra eigenvalues to construct this approximated Gaussian free field. And also, you can see these eigenvalues changes drastically around the edge of spectrum. And if you have a good eye, then there's you can see the distribution function of Gaussian random variable. So, but that can be proved by central limit theorem, but in the general case, this is because of this, distribution function of Gaussian random variable satisfies the following nonlinear ODE of infinite order. So if you take the nth derivative of this distribution function and then you scale it, then divide by the n factorial and take the summation, then it is equal to f. If you solve this differential equation, then you and if you assume that some regularities between regularities at infinity and minus infinity, then you have this kind of solution. So Gaussian density, convolution of Gaussian density with this characteristic function. But I'm not going to talk about this topic today, but later, and then as I told you before, this is our ongoing project with Nick and Yashin Amiru, that the correlations in conformal field theory can be approximated by the expectation of these random functions in discrete field theory, as long as these nodes are well separated. But today I'm going to talk about the projection of this conformal field theory into the SLE level, and in the SLE level, this Gaussian free field is now becomes to this bosonic martingale observable, and in the Koda case, it is linear combination of argument of SLE map minus driving function, and this argument of WT prime. And in the radial case, this linear combination of this part and this part. And in the radial case, we have this martingale observable has monotomy around the target point Q. So maybe I can skip this this concept, because how we explain this domain Markov property on last Tuesday. But what I'm going to say is, because SLE satisfies this domain Markov property, my field, I mean projected from this this conformal field theory, will satisfy this field Markov property. So with this parameterization A and B, A is square root of 2 of kappa, and B is A times this 4 over kappa minus 1, and I'm going to modify by Gaussian free field like this, and then give this boundary condition. So when kappa equals 4, this is the height gate function introduced by Odell Schramm and Scott Sheffield. And then I'm going to project this one in philosophical way. So I'm going to project this one by this conditional expectation kind of thing. Then this process will be a local martingale. But throughout the rest of my talk, I'm going to explain this philosophy in a very rigorous way. So correlation of this field in conformal field theory, given that this SLE curve is the correlation function of field on the SLE domain. So that's the field Markov property, and I'm going to state this field Markov property in a rigorous way, and then outline the proof of this main result in caudal case and radial case. Okay, then let me introduce some basic notions in conformal field theory. So the field we are going to deal with is the following focus space field. So they are constructed from the Gaussian free field in a simply connected domain by applying the following three basic operations. So we take the derivative. So for example, two-point function of Gaussian free field is Green's function. So derivative means you can take the derivative within correlation functions. So for example, correlation function of derivative of phi, which is current field, is derivatives of two-point function of Gaussian free field. Then because Gaussian, then you can compute in the following way. So here W is the conformal transformation from the simply correct domain to the upper plane. Then it has this form. And also we can take the Wick's products. So we treat this focus space fields as formally Gaussian random variables. So we put this Wick's structure on focus space fields in this like this. So they have trivial one-point correlation function. So that means expectation is 0, but this expectation means correlation function. So so this one is product of these two fields minus correlation functions. Then this correlation function is trivial. So if they are centered, which means trivial correlation functions, then if you take the Wick product, then it is also centered. And finally, we take the a linear combination over scalar functions, which is smooth functions. So, but let me explain these Wick products in the next slide. This. So Cauchy is, you can think of this Cauchy as a genuine Gaussian random variable, or Gaussian free field, or derivative of Gaussian free field. Suppose we have a Wick product of these three guys, and the other weak products here, then how can you compute these guys? So if there is no contraction, then you can take the weak product of all of them, and then there is one contraction here. Then if these are paired, then we can bring them with this with taking these correlation functions, and then leave unpaired one as weak products. And suppose we have two contractions, then these are computed like this, and 3 contractions, then there is no weak part. So basically, we give these weak structures on focus space fields. So we have these natural products here, but the product that physicists consider is the following OP products. So let me explain what OP products means. Suppose I have 2 holomorphic fields. Holomorphic fields means that if you take the correlation functions with the other fields, then that's the function of zeta, and this function of zeta is holomorphic except for this node of this field. Then within correlation functions, then you can take the Lorentz expansion. Then these coefficients fields are called OP coefficients, but in particular, the first regular term is called by these OP products. So let me give you one simple example. So the product of current fields is weak product plus correlation functions, and then and these correlation functions can be computed in this way, where W is the conformal transformation from the simply connected domain to the upper hyperplane, for example. Then you can compute, you can expand this one around zeta equals z. Then we have this term, and then the extra term is minus 1/6 of Schwarzschild derivative of z plus this regular term. So that's the regular term, and this is called OP square of current. So OP square of current is weak square plus this Schwarzschild derivative. Then this Schwarzschild derivative is 0 if you take the W is identical map from in the upper hyperplane. But in the upper hyperplane, these objects are the same, but in general, they are different because this is 2-0 differential, but this is Schwarzschild form.
Sorry, what is the meaning of this dot checker?
That's the weak product. That's the weak product. So that means, so by definition, this one is the usual product minus correlation function, so that the correlation function of this is 0. That's how we define this weak product. So we have 2 different structures. This weak product and this OP product. But this OP product is the product that physicists consider in conformal physics theory. Then this OP scale of Gaussian free field is weak square plus 2 times logarithmic conformal radius. And also, if you take the Wick's OP exponential, then you can write in terms of Wick exponential, and the extra term is conformal radius to the power alpha. And then it is convenient to think of this planar domain as a Riemann surface, which has conformal structure. That means we have for overlapping chart phi and phi tilde, then this transition map from here to there is the conformal transformation. Then by definition, a random conformal field is an assignment of smooth function to each local chart phi. And a random field f on this Riemann surface or planar domain with this complex structure is called the differential of degree lambda lambda star. If you read this non-random field at chart phi and the other chart phi tilde, then they have this relation in terms of transition at h prime. So these degrees appeared on the exponent of this relationship. And of course, we also need conformal invariance notion in conformal field theory. So my focus space field is a linear combination of basic field which coming from Gaussian free field with derivative and weak product, and general focus space field is a linear combination over these some smooth functions. But this x alpha is obviously conformally invariant. But in order this field to be conformally invariant, this coefficient function to be conformally invariant. So let me define this non-random conformal field is invariant with respect to some conformal transformation, tau over m. If for any local chart, if you read this conformal field at this chart is equal to if you read this f at the other chart from this automorphism tau, then we call that this conformal field f is conformally invariant with respect to this tau. And of course, this field is conformally invariant if and only if these coefficient fields are tau invariant. And it is well known that if you take the OP product of two conformally invariant fields, then the resulting field is conformally invariant. Okay, so we treat this stress tensor in terms of rederivative. So I think that's the most important slide in my talk. So this field X has a stress tensor, a pair of quadratic differentials A plus and A minus, if the following local word identities holds. In the left-hand side, I take the Lie derivative of this field X. So let me explain this Lie derivative first. So given this local chart phi, I'm going to change this conformal structure slightly according to this local flow of this vector field V. Then I'm going to change the infinitesimal change of these values at t equals 0, and that's the Lie derivative. And then, so that's the geometric quantity of this field. Then it is equal to, so then this stress tensor is the response of this Lie derivative in this analytic way. So within correlations, this field has, because A is quadratic differentials, so holomorphic differentials, A plus, so it has a pole at this point Z, so we can compute the legit calculus. So then this legit calculus produce this Lie derivative. Then that's the definition of definition for this X to have stress tensor is A plus and A minus. Okay, then F of W is the family of fields with this stress tensor A plus minus. Then the most important example is Gaussian free field has a stress tensor. So A plus is weak product of current field. Current field is derivative of Gaussian free field. And A minus is this conjugation. That can be shown by, of course, you can use this local word identity, but equivalently, if you compute this word OP, so that's the product of this A and phi, then by Wick's rule, you have minus of this correlation function times J, then it has this singular OP. So Gaussian free field has this stress tensor. And it is well known that this word family closed under differentiation and OP multiplication. However, this A itself does not belong to word family. So A does not have stress tensor as A, but however, from this property, if you take the weak OP product, which is this guy, then this T, the bilateral field belongs to this word family.
When you say the relative of the Gaussian field, you mean in this direction, or just like Laplacian to the?
And then, so in general, if you take the Lie derivative of lambda star derivative,
Use the white chalk.
Yeah.
yeah. So then we have this formula. So if X is a Gaussian free field, then Gaussian free field is 0, differential. So in this case, my Lie derivative of this Gaussian free field is derivative of Gaussian field is J, and we have V bar and V bar. So given the vector field V, we have this formula, for example. So then this field is called bilateral field for this word family if this bilateral field belongs to this word family itself, and T minus is a non-random holomorphic Schwarzschild form. Then from this setting, one can prove these word equations in the global setting. Suppose my A is continuous and real on the boundary, including the infinity, and X is the product of lambda and lambda star J differentials in this word family. Then if you insert this stress tensor into the correlation functions, then it behaves like these differential operators acting on these correlation functions. So let me explain why this happens. So that's the Lie derivative of differentials, right? If you take the V is the Caudal-Lubner vector field, then this is the Lie derivative of correlation function of this X. And let me explain how this left-hand side is converted to this right-hand side. So let me introduce this word functional. So by definition, word functional, if my word functional acting on product of field, then it is let's the sum of V A and then A plus, but in this case A plus is A, and but if we define word function like this definition depends on the field we are going to apply. But by the Green's function, Green's theorem, then you can rewrite this action as this in this uniform way. Then in the upper plane, my stress tensor can be written as word functional applied to this Caudal-Lubner vector field like this. Because if you compute this one for this vector field, but if you plug reflected vector field here, then and then if you add these two terms, then this term cancelled out because my A has real on the boundary. So and for this term, my vector field is holomorphic in the hyperplane, so this d derivative is 0. But if you plug this one into here, then you got Dirac mass at this pole, so which gives you this A. So if you insert this stress tensor, then it is the same as insertion of this word functional. And then if my fields are in the word family, then this word functional is going to Lie derivative. The Lie derivative, in the differential case, my Lie derivative is computed in this way. So that's the word equation. But to define one-leg operator as a OP exponential of holomorphic part of Gaussian free field, we need to define this holomorphic part of Gaussian free field as integral of this derivative of Gaussian free field. So that's the multi-valued field. So that's the beauty part of this conformal field theory. So given 2 points, my pi plus of z from z naught to z is the this one from all paths from z naught to z. So this is a multi-valued field. But in the upper plane, the correlation function of current has this form, and if you integrate this, then correlation function of this multi-valued focus space field with this J has this form. But if you integrate one more out, then this correlation function between pi plus with these points is the logarithmic of cross ratio. Of course, it depends on the path we are going to take from z naught to z. So for example, if you take the path gamma from z naught to z in this way, and then gamma tilde from z naught tilde to z tilde in this way, then it will give the same correlation functions, because if you take the difference, then you need to integrate this out along this path. But the winding number of this z is this 1, and winding number of this around z naught is 1, but if we take the difference, so it is the same. It becomes 0. So in this case, these correlation functions are the same with this pair of curves. Okay, then we generalize this concept into the formal level. So my formal field is a linear combination of pi plus, which is holomorphic part of Gaussian free field, and phi minus is anti-holomorphic part of Gaussian free field. So with one node, they are formal fields, which have the following formal correlations. So 2 point of phi plus is log of 1 over j eta minus c. In the radial case, correlation function of phi plus and phi minus has this form, and in the radial case, we take this, so that addition of this holomorphic part and anti-holomorphic part gives you Gaussian free field, and anti-holomorphic part is just conjugation of holomorphic part. But the most important thing is this field is, of course, from the beginning, this is a formal field. In many cases, it does not make any sense, but this one is well-defined focus space field if and only if you take the summation of these coefficients, the charges, are equal to 0, then you can think of this one as to be a well-defined focus space field. For example, so here we have charge 1 and charge minus 1 here, so the total charge is 0. Then this field is just this integration of this current field. So this is a well-defined. We can think of this one to be well-defined focus space field. And if you take the pi plus and phi minus here, then tau is 1, and minus tau is plus 1. So tau star is minus 1. So it satisfies neutrality condition. But in that case, this addition is just Gaussian free field, which is well defined. But I'm going to and I want to construct a field of this tau and tau star, so that they are divisors. So this one has this weak part, which is linear combination of bosonic field, and the correlation part is will be explained later. And this OP exponential satisfies Ward equation. And then this field can be interpreted as an OP exponential of background charge modification of this bosonic field. So let me explain this correlation part first. So B is a background charge parameter. So at this moment, B is any real number. Then the sigma is a divisor. So you can think of that as just a complex atomic measure at these A's. And then I pick this lambda J, which is conformal dimension of these differentials. So then I'm going to define this Coulomb-Gas correlation function of this divisor in the following way. So in the complex plane, this one is a product of this difference of these two nodes to the power, the product of these charges in the identity chart at a finite these points. If these points are finite, and if this point is infinity, then I take this inversion chart. And then I require that this function is lambda j differentials in each GJs. Okay, so this part is well-defined focus space field if and only if these charges satisfies this neutrality condition. But this correlation function is Möbius invariant if and only if the summation of these charges is equal to 2 times B, where B is the given background charge parameter B. So there are two kinds of neutrality conditions. So how can you reconcile these to these guys? But let me extend this notion to simply connected domain by reflection. So suppose we have two divisors, then I reflect these divisors in this way, and then for the simply connected domain, I define these Coulomb-Gas correlations with this divisor and reflective divisors. So for example, in the upper plane, we have this simple form. Okay, so in the Kolar case, SLE curve describes the random curve from the marked boundary point to the another marked boundary point. But in the radial case, this curve starts from the marked boundary point to this marked interior point. Okay, so now I'm going to define this this field O. So a weak part has this. So that has weak exponential of this bosonic field with neutral condition NC0. That means all charges are equal to 0, summation of all charges. And then we define this Coulomb-Gas correlation functions, but this tau and tau star satisfies neutrality condition 0. So I need to put extra charges at these marked ending point. So this correlation part is a ratio of these two correlation functions with extra charges 2b at q in the caudal case. In the radial case, I put a background charge b at q, and in the reflected charge also b at q. Then these correlation functions satisfy neutrality condition NC sub b. So all charges, the summation of all charges are equal to 2b. And also you can compute, conformal dimensions at the other points are the same, but the conformal dimensions at this marked boundary point in the caudal case and marked interior point in the radial case will become like this way. So then you can think of that as a OP exponential of this guy. Okay, but it can be realized in the following background charge modifications. So in the corner case, that's my Gaussian free field with B equals 0. And then the B is the central charge, background charge parameter B. Then I'm going to add this non-random function to the Gaussian free field, where W is the conformal map from the simply connected domain to the upper F plane, sending Q to infinity. And of course, W is not unique. However, this argument of W prime does not depend on the choice of this W. Now, in the radial case, instead of this, I'm going to add argument of W prime over W, so that this one does not depend on the choice of W. And then for the general value of B, I define the Virasora field as the OP square of current field plus this constant times derivative of J. Then in the radial case, the Gaussian free field has an additive monodromy around the endpoint of radial SLE, radial SLE, and this Virasora field has a double pole at Q. That's the main difference between caudal conformal field theory and radial conformal field theory. Okay, then how can we get a boundary condition changing operators? So I'm going to insert this one leg operator in the caudal case. So I put charge A at the starting point, and I'm going to put charge minus A at the end point. So then neutrality condition is satisfied. So then under this one leg operator over its correlation function, so that is just this Wick's exponential of pi 0 plus from P to Q. Then if you compute this, then by Wick's calculus, of course, this exponent came out, and the only non-trivial term is correlation function of this one and this. And of course, that is computed in this way. It is difference of complexified Green's function. But my W is a conformal map sending P to 0. So this term is cancelled out. So you have 2A times argument of W from this term, and WQ is going to infinity. So this term cancels out. So that's how you get these height gap functions developed by Schramm and Oded and Sheffield, Scott Sheffield. But in the radial case, it can be done by inserting this one leg operator. So I put charge A in the starting point, and charge minus A over 2 and minus A over 2 in the marked interior point. So under this insertion, my Gaussian free field has this boundary conditions. Okay, so let me introduce the main theorem in the caudal version. So F sub B is the OP family of this modified Gaussian free field under this OP multiplications and linear combination over scalar field C. And then I'm going to take the this parameter A to be square root of 2 over kappa. Kappa is the SLE parameter. And background charge parameter is A times 4 over kappa minus 1. And if my fields in this conformal field theory, I mean the OP family of this phi sub B, then the following non-random fields, which is correlation function of these fields under insertion of one leg operator, are martingale-observables for caudal SLE kappa, which means if you read this non-random field at this SLE domain, so D sub T and gamma sub T is the tip of SLE path, and Q is the target point of SLEs, then this process are local martingales for Radial SLE form. So this is a well-known statement in physics level, and this theory was developed by Bauer and Bernard and Cardy's group and Wigman's group. But we present this theorem in a mathematical way, and that's the sketch of proof. So G sub t is the SLE conformal map, so which sends T of SLE curve to the driving function. Then here we take the P to be the starting point of SLEs, but I just translate into Xi, and where Xi is in the real line. So that's the insertion of this one leg operator from Xi to Q. Then this process M sub t can be written as in the following way, due to the conformal invariance of this field in this OP family. So M sub t can be written as this R sub t, R sub Xi. When you read this R sub Xi at this chart is just inverse of this Rubinov map. Then we are going to compute the drift term of this Ito derivative of this M sub t. And of course, if you differentiate this one, then you have d Xi squared, half of this, and then square of this term here. And then also you need to compute the infinitesimal change of this M with respect to this Rubinov map. It will give you this Lie derivative of this correlation functions. So that's my drift term. Then it will turn out to be 0 at the end. But let me explain why. So drift term of this dm sub t is equal to 0 by the Cardy equation. But Cardy equation is combination of Ward equation and level 2 degenerate equation for a one-leg operator. So Ward equation means if you insert this Virasora field, then Virasora field is acting like this Lie derivative. That's the Ward equation. So and then let me explain these two level 2 degeneracy equation. So within correlation functions, my Virasora field has this mode expansion with Virasora generators L sub n. Then this Virasora generator L sub n represents the following well-known Virasora algebra. So Lie bracket has this representation. But level 2 degeneracy equation for this one-leg operator from Xi to target point Q, if you choose charge A to be square root of 2 over kappa, then L minus 2B, which is OP product of Virasora field and one-leg operator, is equal to kappa over 4 times L minus 1 squared B, but L minus 1 is differential operator. So combining these two Ward equation and level 2 degeneracy equation, we got the following Cardy's equation. So which means if you take the second derivative of this correlation function with respect to Xi, then you get this Lie derivative of this field within a change of this correlation functions under the insertion of one-leg operator. So let me compare a Koda case and radial theory in the following next few slides. The Virasora field has this form. In the Koda case, Virasora field can be written as this stress tensor. If we take the stress tensor has trivial correlation, then T is A plus this Schwarzschild derivative. But in the radial case, we have extra term, so which has a double pole at the target point. And I choose vector field V in the Koda case as the Koda Lubinov vector field, and in the radial case, I take the radial version of Lubinov vector field here. And for the word functional, so suppose if I take the just one field here, then it gives you this legit calculus of this integrand in the caudal case. But in the radial case, this term is word functional at the functional disk, functional domain. Then also we need to consider word functional at the target point, which gives you this extra term. So in the radial case, we need to consider target point, like this. But then, my bilateral field can be, in the upper plane, my bilateral field can be recovered from word functional in this way from, in terms of this Lubner vector field. In the radial case, also it can be recovered, but we have extra term 2 zeta squared, which comes this numerator. But however, in the caudal case, word identity means this word functional can be replaced by this Lie derivative within the correlation of fields in conformal field theory. But in the radial case, that happens up to conjugation of this background charge operator, which is Coulomb-Gas correlation function with charge V and B at Q's. So that's the minus 1/2 B squared minus 1/2 B squared differential with respect to this target point of radial SLE. And also that is identically 1 in the identity chart of this unit disk. Then combining these all theories, then we get this Cardi's equation in the caudal case, and also the radial case, we have this Cardi equation. That it will give you the main theorem in a radial version. So in the radial case, we extend OP family by adding the OP functionals at the target point of radial SLE, which is Q. So for example, X sub Q is OP product of field at punctured disk, punctured domain, and constant field 1. And we denote this one, the extended OP family. Then this family contains this OP exponentials with non-trivial charge at this marked interior point Q, and also current at Q. Current at Q can be computed in this way, and you can compare this computation in the other point, which is not equal to Q. So J is J at B equals 0 plus this pre-separation form, but at Q, these coefficients is reduced by 2. So we also include these kind of fields in the conformal field theory. Then, if X is any string in the extended OP family of modified Gaussian free field, then the non-random field, which is insertion of one leg operator of this correlation function, is going to be a martingale-observable for radial SLE cathode. And also, one can modify this one leg operator like this. So we are going to consider spin S. So in this one leg operator with a spin, I'm going to put charge A at P, and also different charge at Q's. But these charges, of course, satisfies the NC0 neutrality condition. But I'm going to take the delta to be 2s over A, so that this spin, which is difference of conformal dimensions at Q, is equal to S. Now, under insertion of this one leg operator with spin S, my Gaussian free field becomes modified Gaussian free field without spin plus I delta times log of W. So under the insertion of this one leg operator with spin, the correlation function in the extended OP family forms a radial SLE kappa with drift term eta, and eta is given by this relation. So So we have complete understanding of this radial SLE kappa with this drift term. We have this martingale-observable for this version of radial SLE. Okay, so let me skip this. Maybe I need to skip a few slides very quickly. So let me explain our ongoing project a little bit more. So with Nick and Kang, we are doing conformal field theory of multiple SLEs. So multiple SLEs describe multiple interfaces with this Lubner equation, where this deriving function satisfies this stochastic differential equation, and this coefficient is logarithmic derivative of this partition function, and this partition function satisfies the following null vector equation. So, for example, if you put charges everywhere, charge A on the everywhere, then you expect multiple SLEs from this point to the infinity. But if you consider screening variable here, and then put charge minus 2a here, and then integrate out this screening variable, then you will expect multiple SLEs connecting these 2 points like this. But our project is find all solutions of these null vector equations, and then implement the corresponding conformal field theory of multiple SLEs. And also it is very interesting when kappa is equal to 0. When kappa equals to 0, this multiple SLE zero map is just defined by this differential equation. But now this function u is going to satisfy the following algebraic equations. So for example, n equals 4, we have these particular solutions. So u sub j is, so this term coming from this configuration. But if you have extra term like this, so q sub 4 is this algebraic function. Now in that case, our multiple SLE is 0, starting from, so we have two types of these solutions. So x1 and x2, x3 and x4 here, then one of these solution gives you, describe the multiple SLE from here and there, then they are going to merge at this top, and the other one gives you this picture. But so far we have the following theorems. So one class of solutions are given by this. So the trivial solution, kind of trivial solution, plus extra term, and this one is called stationary point, and stationary point satisfies the following algebraic equation. Then this one gives you solution to null vector equations at kappa equals to 0. So then our project is find this complete solution to this null vector equations at kappa equals to 0, and classify geometry of classical limits. So for example, what's the connectivity of multiple SLE zeros? So you can have this or this. So for example, if you have just one stationary point, then suppose you have stationary point between these two points x2 and x3, then my classical limit of SLE kappa, which means SLE 0, is going to be merged like this, and the other point is going to infinity if you have one stationary point. But anyway, in the general case, we have kind of SLE 0 martingale-observables, which has this one. Okay, now go back to the last slide. Thank you very much, and happy birthday.
Other questions?
Oh, which one? Go ahead.
Tom?
So what are some of the radial martingale observables you can describe? Like some of the ones that SLE ones that have already existed.
Oh, so I tried to give you some trivial examples. So, for example, so here is the full description of vertex observables. But in the one-point vertex fields, and then we are considering the real vertex field, one-point field. Then that happens if and only if these two. So because one-point vertex field has essentially two charges at point Z and point at target point. So that is real and if and only if these two charges are equal to each other. But by the neutrality condition, because the summation of these all charges are equal to 0, so this tau sub q should be minus tau. So essentially we have just only one type of one-point vertex field. And then the interesting case is if tau is minus a, then this term is going to 0, so there is no covariance at q. And in that case, you have this kind of observable. And you with Michael and Greg found out that this kind of one-point vertex field without this covariance at q at kappa equals 4 is the Beckman's type observable for radial SLE. So I mean, in the well-known cases, so martingale observables can be found found through the correlation functions in conformal field theory by matching conformal dimensions at some point Z and also at target point. Was-Green method.
Right. I think that one.
You have once you construct you have constructed this theory. You have a way, for instance, to derive the Cardis formula for SLE6.
Oh yeah, yes. Yes. In the Kohler case, yes, we have an explanation for Cardis from this correlation functions in conformal field theory.
Oh no. Any more questions? So let's thank the speaker again.